Here's an example of basic polar graphing. We're gonna do a little bit of this mixed in with the conics, and it's gonna get us ready for some other kinds of graphing like parametrics. And it's a good review of stuff that connects with last semester with the trig. So here's polar graph paper. Remember, polar coordinates r is the distance from the origin, so this is r equals, this is going to be 8. It's going to be in 2's here. R equals 2, 4, 6, 8. And then theta, the radial lines are various values of theta. So this is theta equals 0, theta equals pi over 2, theta equals pi, here's theta equals pi over 4. I have it marked out in pi over 12. So pi over 12, 2 pi over 12 is pi over 6, 3 pi over 12 is pi over 4. We're not going to make much use of the pi over 12s because we don't know the trig values by heart for those guys. But it just makes a more uniform graph paper. So here's the equation we want to graph. R equals 4 plus 3 sine theta. What kind of shape is that going to make? Well, we're not going to try and do anything sophisticated this time. We're just going to plot points. So we're just going to plug in values of theta, get the corresponding r from this function, make a table of theta r values, and then plot the points. Okay, so let's start doing that. If theta equals 0, then sine of 0 equals 0, and so r equals going to be 4. Make that math mode. If theta is pi over 6, then sine pi over 6, think about that for a second. It's one of those ones that you want to have memorized. That's going to be 1/2. 4 plus 3/2 is going to be 5.5. Then it gets a little more complicated. We're going to get 4 plus 3 times root 2 over 2. Because sine of pi over 4 is root 2 over 2. When you evaluate that numerically, it turns out to be about 6.1. Okay, so we can start go ahead and plotting those points on our graph. Let me show you what's happening there. As we make things in the table, we can look at how that plots. Here's the first two. Here's theta equals 0, so that means you go out in the standard plus x direction, that's theta equals 0, and you go out 4 units. Remember, these are units of 2, just because I didn't want to have too many circles, it would be too busy. So 2, 4. Then pi over 6. We're skipping this one because it's pi over 12, and we could do that with a calculator, but we don't really need to. Pi over 6 is up here, and we went out 5.5 units. 2, 4, almost to 6, but not quite. Then the next one is going to be up here at pi over 4, and just past, it's going to be just a little bit past the 6 ring for 6.1. Let's just do a couple more, though. This is going to be 4 plus 3 root 3 over 2. And when you evaluate that numerically, it turns out to be 6.6-ish. And then pi over 2 is nice and easy. Sine of pi over 2 is 1. 4 plus 3 is 7. Okay. So what we can see is that it's going outward. It's going gradually outward, and it ends up at 7 units away when it's in the vertical direction. Theta is pi over 2, r equals 7. It's going to be up here between the 6 ring and the 8 ring. We can continue that, and let's see what my next picture is. Yeah, so here's that all the way up through pi over 2. Now let's look at what happens when we go to 2 pi over 3. Here's where we start to see some patterns. Sine of 2 pi over 3, that's the same as sine of pi over 3. So we're going to get 4 plus 3 root 3 over 2. Well, that's the same number as we got for pi over 3. There's a symmetry here. It's going to be exactly that 6.6 number. Oops, just kidding. There we go. Similarly, 3 pi over 4, the sign is going to be the same as this guy. So it's going to be easy to write these numbers down. 5 pi over 6, the sine of 5 pi over 6 is the same as sine pi over 6. So we're going to get the same numbers we got there. So this is fairly common. Simple functions of theta often give us symmetries. And so we're going to get something that's going to be symmetric about the y-axis because this goes out in the same pattern that it goes in as the angles go between pi over 2 and pi. So at pi, in fact, we're down to back to 4 because sine of pi is 0. Okay. And so we're going to get a nice symmetry. I think that's the next picture I had ready for you. Yeah. We plot these points, 1, 2, 3, 4, 5, 6, 7, 8, 9. And these guys are not so hard because we start to realize they're just symmetric to these guys. So it's gone out a bit and then come in. What's going to happen over here? Well, I'm not going to do that laboriously for you. Let me just cut to the chase here. When the sign becomes negative, sine theta is negative down here. Now these numbers become less than 4. 4 minus 3/2 becomes a 2.5. These numbers, The smallest number ever going to get is when theta is 3 pi over 2. Because when theta is 3 pi over 2, that's when sine is minus 1. It's the most negative it ever gets. 4 plus 3 times minus 1. 4 minus 3 is 1. And that's the closest we're ever going to get to the origin. Again, you can see the symmetry. There's a lot of these numbers are the same. And what that turns out to give, let me show you the final graph, is this curve that goes out from 4 to 7, back down to 4 units away, and then it comes in and it gives us a little dipsy-do here. It's kind of a lima bean shape that it comes dipping in just under 2 here at 1.9. 5 pi over 4 is 1.9. And then it doesn't just kind of come across like a circle. It's very much not a circle. It actually dips in significantly here to give this 1, which is pretty close, halfway between 0 and the 2 ring. And then symmetrically comes back out through about 1.9 out to 4 units. And so that's an example of polar graphing, where we just plotted points theta r, and we took it around and we got this nice closed curve that's a funky, unfamiliar shape. There's a lot of polar graphs that are kind of novel shapes that we haven't seen. One of the things we're going to see is that if you take a slight variation on this, that unexpectedly we're going to actually come back to our conics, and we're going to see parabolas and ellipses and hyperbolas. We're not going to have a lot of time to spend on it, but it'll be pretty cool how those come out.